So we're going to continue the homework on our KSP stuff. We're just going to be doing, I think we'll see how long this takes, and then we'll see how much we can cover in this video. But so now we're going backwards. We're trying to, before the last video, we were given molar solubility, we were given concentration at saturation, concentration at equilibrium. We were asked to calculate KSP. Now we're going backwards, which is essentially not that difficult, because we know that we're going to write our same expression here, Ag plus Cl minus 0, 0 plus x, x. But just here, molar solubility in a saturated solution, so our KSP is going to be equal to x squared. We have to calculate that when we're given KSP. KSP is 1.8 times 10 to the power of negative 10 is x squared. So we take 1.8 times 10 to the power of negative 10, take the square root of that, and our x, which is our molar solubility, is 1.34 times 10 to the power of negative 5. How many formula units are dissolved in 1 liter? So again, we want to go from, we have calculated our x in moles per liter, moles per liter. So this is number of moles in 1 liter. We're going to multiply that by 1 liter of solution. We're also going to multiply that by 6.022 times 10 to the power of 23 formula units per mole. So to get times 8.079 times 10 to the power of 18 formula units. What is mass percent per m per v? So again, I already have my divided by volume, so essentially I'm going to do this over here. I start off again with 1.34 times 10 to the power of negative 5 moles per liter. And I'm just going to convert moles to grams, which I have to do by finding the molar mass of AgCl, which I will conveniently find to be 143.32 grams per mole. I can't write grams. So this is 1.34 times 10 to the power of negative 5 times 143.32 grams is 1.92 times 10 to the power of negative 3 times 100, which is a solubility of 0.192%. Mass per volume solubility. Okay, so again, KSP is given, calculate molar solubility. Write our equilibrium expression. Zero, 0 plus x plus 3x, x, 3x. KSP equals x times 3x cubed. Remember, it's cubed. 3 cubed is 27. X times 27, x to the power of 4, which is equal to 27 x to the power of 3, which is equal to 27 x to the power of 4, which is equal to our KSP, which is 2.8 times 10 to the power of negative 39. So we'll do 2.8 times 10 to the power of negative 39 divided by 27, and then take the fourth root of that to give me an x value of 1.01 times 10 to the power of negative 10 moles per liter, molar. And that is my molar solubility. Okay, the same idea in moles per liter and grams per liter. That's not too bad. Zinc iodate is, again, zinc plus 2IO3 minus 0, 0 plus x, 0, 0 plus x plus 2x, x, 2x, x times 2x squared equals KSP, which implies that 4x cubed equals 3.9 times 10 to the power negative 6, which means that x is my molar solubility, is 3.9 times 10 to the power negative 6 divided by 4, and cube root of that answer. So cube root is 9.916 times 10 to the power of negative 3 moles per liter. That's one answer. And then just to convert that to grams per liter, I have to times it by 1 mole, and how many grams? Zinc iodate. Zinc iodate 415.2 times 415.2 gives me an answer of 4.117 just 4.177 grams per liter. Formula units of zinc sulfide that can dissolve 1 liter solution at 25 KSP is given. Okay, so we're running formula units. Whoops, I have to charge. Okay, so we are going to continue. I don't know why that was popped. Okay. Formula units, again, maximum number, you can see solubility, molar solubility, formula. All of this means that we're calculating our x value at equilibrium, right? So here, what do we have to do? Again, find our x, zinc sulfide. I'm going to skip some steps here. Zinc sulfide, zinc 2 plus. I'm not skipping any. Well, okay, here's my skipping steps. 0, 0, plus x, x, x squared equals KSP, which equals 2 times 10 to the power of negative 22. So x equals 1.414 times 10 to the power of negative 11. That is my molar solubility. So this is in moles per liter. Maximum number of formula units that can dissolve in 1 liter of solution. So I times this by 1 liter, which doesn't do anything. And then I also times it by 1 mole and 6.022 times 10 to the power of 23 formula units, which equals take the square root times 10 to the power of 22. And do times 6.022 times 10 to the power of 23, which is, I did something wrong there. Whoops. There, 8.516 times 10 to the power of 12 formula units is my solubility of this solution. So this was a short video, so I think we'll continue with the common ion effect because we only have this much, just a couple of questions to answer. Again, it's just comparing molar solubility of different substances in pure water and 0.15 mole of an common ion. So again, molar solubility of AgCl. So we'll do this. We're going to do again AgCl. What was given to us? 0.15 mole per liter. Okay. So in pure water, first case, pure water. In water, we had again 0, 0, plus x, x, x. X equals x squared equals KSP. So our x value equals square root of KSP, and the KSP can be obtained from the back of the textbook for silver chloride as 1.77 times 10 to the power negative 10. So part 1, x, or molar solubility in pure water, equals square root of 1.77 times 10 to the power negative 10. is 1.33 times 10 to the power negative 5. The next case we are going to do, we're just going to modify this a little bit. We're going to say part 2, and that's 0.15 NaCl, 0.15 NaCl, which basically, again, soluble salts is 0.15 molar Na plus and 0.15 molar Cl minus. And the thing we're concerned with is the Cl minus, because that's what affects this equation right here. So instead of 0, this is going to be, well, this is part 2, right? So this is all part 2 stuff. So instead of 0, this is going to be 0.15, 0.15 plus x, 0.15 plus x. So we just do a quick 0.15 divided by KSP greater than 500 justified step to cancel out this plus x. So our new KSP, our new expression, will be x times 0.15 equals 1.77 times 10 to the power negative 10, which means our x in NaCl is going to be equal to 1.77 times 10 to the power negative 10 divided by 0.15, which is 1.18 times 10 to the power of negative 9. As you can see, solubility decreases in a common ion when there's a common ion present, right? Hopefully that was okay. You can just rewind, I guess. Okay, so that was that question. Similarly, we can answer multiple questions in a very similar fashion. 22 is lead iodide in 0.05 moles per liter of NaI. Again, lead. And our concentrations of lead are going to be, well, 0, and an initial concentration of iodide is going to be, again, here, this is basically 0.05 Na plus and 0.05 I minus, and we're going to use the 0.05. We don't care about this because it does not affect this system right here. So this is, instead, our initial concentration is going to be 0.05. Again, the same Haber plus x plus 2x, x 0.05 plus 2x, 0.05 divided by KSP. So what is the KSP? Is that given to us? No. Lead iodide is 9.8 times 10 to the power of negative 9. It's greater than 500 justified. So cancel out that 2x. So I get 9.8 times 10 to the power of negative 9, which is my KSP, is equal to x times 0.05. So x equals 9.8 times 10 to the power of negative 9 divided by 0.05. 1.96 times 10 to the power of negative 7 is my molar solubility of lead iodide in that concentration of sodium iodide. Okay, molar solubility of calcium sulfate. Okay, that's another easy one. Yeah, there's another easy one. Okay, so let's do, again, we're asked both cases, so we're gonna write case 1, pure water. What is my KSP of calcium sulfate? Back of the textbook, 4.93 times 10 to the power negative 5. So my x, which is molar solubility in pure water, is square root of 4.93 times 10 to the power negative 5, which is 7.02 times 10 to the power negative 3. Next, my second part is in... Oh no. No, why did that happen? Can I undo and undo? Back. That did not help at all. Okay, we're going back to the beginning here. And that doesn't pop up. Psi, okay, I'll write it again. Calcium sulfate. Oh, first we have to see what our ions were. Hopefully this is loaded in the meanwhile. And of course it hasn't. I think we're on somewhere close to that page. Okay, we actually started working, but I forgot to hit record, so we're going to quickly review what I have written here. So I was trying to answer the last question with calcium sulfate, and I didn't get there because I erased it. So I'm going to do that again over here. That's where we left off, our calcium sulfate. Again, so this is going to give me, the sodium sulfate is going to dissociate completely to 2 sodium plus and SO4 2 minus. So if I have 0.25 moles of this, I have 0.5 moles per liter of that because I have to multiply it by 2, and 0.25 moles per liter of the sulfate ion. And in my equilibrium expression here that I'm worried about, my calcium sulfate, I'm only worried essentially about my sulfate ion. I don't really care about my sodium because it's not affecting this. Plus x, x, 0.25 plus x. KSP of calcium sulfate was 4.93 times. So 0.25 divided by KSP is greater than 500. Justified. So here I have my answer as in x times 0.25, because I canceled out that, equals 4.93 times 10 to the power of negative 5. So my x is just this divided by 0.25. Which is 1.972 times 10 to the power of negative 4. And we saw that that's lesser than my molar solubility of calcium sulfate in water, which is something to the power of negative 3, I think. But yes. So our last question, we're gonna go. I've already started writing again. I forgot to start recording when I started doing the question. But in pure water is in red basically. So we did that calculation. So we have our lead chloride. Let me change. We have our lead. This was our equation in pure water. It was 0, 0 plus x plus 2x, x, 2x. KSP, which was given to us, is this is x times 2x the whole squared, like so, 4x cubed. Divide this value by 4, take the cube root, I get this answer. Now part 2, in 0.1 molar calcium chloride. Now we know that this calcium chloride is going to split into 1 calcium ion and 2 chloride ions. So 0.1 moles per liter of calcium chloride is going to give me 0.1 moles per liter of calcium, because that's a 1:1 ratio, and 0.2 moles per liter chloride ion, because that's a 1:2 ratio. 1 over here. And therefore you have to double the concentration of chlorine, which means that instead of 0 here, it's going to be 0.2, 0.2 plus 2x, 0.2 plus 2x, and then we do our quick 0.2 divided by KSP greater than 500, justified, check. To cancel off our 2x, this is just 0.2, so our KSP 1.6 times 10 to the power of negative 5 is x times 0.2, so our x value is 1.6 times 10 to the power of negative 5 divided by 0.2, 8 times 10 to the power of negative 5, which is lesser than this in pure water, which makes sense. Common ion decreases solubility of a salt. And there we go. So that was our KSP little calculations. We just have our predicting precipitate left, so that will be the last video. All right, so I'll see everybody in class.